Hello, welcome to my channel. Today I'm going to talk about the evolution of understanding the fractal geometry. I was intrigued as engineering student about mathematics, and basically we were occupied long hours learning from basically books which are published in Russia, because in my home country it is believed that Russian manuals are the best with exercising rigorous evidence for every single theorem. And I discovered about something more novel when I was already finalizing my postgraduate studies as a biophysicist. So I fell in love with fractal geometry and while I was working on my PhD, and it turns out to be a whole new world. I knew of many things, especially of its applications in medicine, through Professor Klonovsky, but I soon returned to him as one of the biggest names in that part of science. So the main name I was aware of was Mandelbrot, and he was a maverick man with very unique life story and the possibility to actually gather all other discoveries in one framework that we are using today. So actually there are a lot of work of mathematicians of 19th and beginning of 20th century that were simply discarded as something too irrelevant to nature. The geometrical figure that they are constructed were simply discarded as something which is artificial, which is not a part of nature, but people were, as many times before, wrong. So the first mathematical description about fractal phenomena was actually Setz, which is stated in 1883, and Peano followed with his work on 1890, when he showed actually how fractal forms are filling in the space. So this is now one of the basic mechanisms how we perceive the notion that fractal geometry has to do with having natural shapes. So after that, in the beginning of 20th century, followed Sierpinski with his triangle, and also the Koch's curve, or the Koch snowflake, as I like to perceive it. So they both published about their thinking of fractal geometry in 1909 and 1912. And soon there was a beautiful mind of Julia in 1917, talking about Julia Setz, but alas, it was not possible to him to see what Julia Setz looks like, because he couldn't have that big computational power that every computer can provide you now. So it is also important to stress another scientist who contributed a lot to what Mandelbrot was formulating as his fractal geometry, and this is Richardson, who was active in 1920s. Mandelbrot said for that particular scientist that he was really interesting personality, and in that period in 1920 there are several people alike who were really bold in trying to do something completely new, living one completely unorthodox attitude towards life, which gave fruit. But although Richardson was that bold that he was actually asking questions nobody else wanted to ask. He basically laid the ground for what Lorentz would later formulate as chaos theory, because he was printed several seminal works in thermodynamics and turbulences. And as an engineer of biomedical electronics, I know about the work which are coming from another side of people who are actually active in physics. And for example, it is very important to understand the application of fractal geometry in analysis of signals or in electrophysiological signals, which is very important for my work in medicine. But it comes from the part of physics where electronics originated. And for example, Schottky was experimenting with cathodes and the signal that you get when hot cathode is actually emitting a bunch of electrons. And electrons emission is actually a stochastic process, and when you record it, this is white noise. But he actually discovered that beside that generally considered stochastic signal, on low frequencies you have something that we call today pink noise. And Johnson decided to confirm and formulate what Schottky discovered experimentally in 1925, but Schottky published mathematical formulation of that in 1926. And then it was World War and Second World War, and since world turned to disruption and destruction, a lot of people who were dealing with science actually had to resolve pressing issues, not to deal with science. But Mandellbrot also had a very unique story. He was actually born in Warsaw. I didn't know that. But his parents, having Jewish origin, had to flee, and they were living in France. And as I remember from reading biography, he actually spent his childhood in Toul, in central France, where he actually didn't go to school because it was very, how should I say, there were a lot of problems and they were in hiding. So he basically didn't go to school as children usually do in that time, in the first 2 years. And then I think it had a great impact on his way of thinking, because it is not the only example of someone who have a very curious mind, but lack that pressing impact of formal education, because they can learn to think unorthodoxly. And he said that he always had a love for geometry and geometrical shapes, and both his father and his uncle were very well-known mathematicians. And yeah, he said that in his childhood he was actually schooled at home. His father taught him to play chess, to learn some basic things from mathematics, but actually he was smart enough to find something which interests him more and educate himself reading and practicing something that which is not usual for that years. And later, when the war passed and he was old enough to enter the university, he basically passed with excellent marks all the exam, and at the best known and the most famous institution in France, School Supérieure, which is a famous place where many mathematicians were actually making the history of mathematics. But after being accepted in such prestigious institution, after a week, Mandelbrot actually figured out that he is going to be narrowly directed on certain things which are a little bit boring for him, and he decided to go to Polytechnic Academy instead, where he had much more freedom in deciding what he's going to deal with and what he's going to learn. And he basically flourished. He went in US. He was spending a summer in IBM, and he was lucky enough to be present when the first computers were made, and that gave him opportunity to collect all the ideas which were made before but couldn't be exercised to the full, and simply scientists like, for example, Julia couldn't actually see how the forms that he formulated looks when you generate them. And after IBM, he was also collaborating with von Neumann, thus giving his contribution to information theory. But although he was active in many fields and giving many contributions, for example, he formulated how you can follow the dynamics in finance. And he said that it was a curious story that once he was invited on department on university to give talk about his work, because he was active in fluctuations and fluid dynamics. And he saw on the table exactly the same form of his work that he still didn't publish. And he asked the colleague, how did you know about that? Who told you this? And he said, but this is the graph of how the prices of cotton are actually rising and falling through the year. And then he realized that it applies also to the market. So one of the most influential part of work that Benamanda had is actually in finance, but he actually revolutionized that the way how we perceive living organisms, their shape, forms, and dynamics. So, to cut things short, Mandelbrot even said that he has an impression that he didn't invent something new, but that he was simply the first person to be able to see what many other people couldn't, because when he used the very primitive machine for plotting actually, he made a graphical representation of Mandelbrot set, of M set. And this is a stunning feature, this is stunning fractal structure, and I think the most famous fractal structure in the world, because many people will recognize what it is about. When you look at the object, it can remind you of many things, many living creatures and shapes. But for example, it can remind you on the cockroach. It is a little bit hairy or wrinkly, and it can remind you, or a cat, or another living creature, or something mysterious but alive, because that fractal object has a feature which you can see in many living organisms. For example, if you use very simple recurrent formula that Mandelbrot formulated, this is simply Z translating in Z squared plus C, and everybody who knows how to add things and how to multiply things can understand that. The formula, simple as this, can give you forms which are repeating and amplifying until to infinity, because Mandelbrot applied that on so many fields. For example, to learn about clustering the galaxies, to learn about the trends in nature, the trend in markets, and what is most interesting for me, when they apply that on human physiology, it turns out to be that many systems that we have actually, I made a mistake, every system that we have in our body actually has a fractal nature. For example, if you look at our alveoli and our branches in our lungs, this is pure fractal structure, fractal tree, and that fractal structure actually gives opportunity to our lungs to have a small volume, but actually the enormous surface. That the same applies to our brain, to our guts. And if you look to any part of our body, you can see that our anatomy has fractal properties. And fractal is also the name that Mandelbrot actually invented, because he had a classical education and he was learning Latin when he was a kid. So he said, I was well aware that I must find a completely new name which would attract attention and which will capture what it is phenomenon about. Because fractus, it means broken, it means something irregular, something which is surprising. And if you learn to see what fractal forms are like, you will never stop seeing fractals all around you. For example, the shape of the tree, the shape of every leaf, the fern is beautiful fractal structure, the shapes of the coast, because one of the most famous articles that Mandelbrot published in 1972 is how long is the coast of the Britain, and it also applies to the shape of the mountains, to the shape of clouds, because he said clouds are not spheres. And if you look at the lightning, it is also a fractal form, and it is beautiful. Everywhere you look, all naturally generated forms are actually fractal. So is the dynamic of our heart, the dynamic of our brain, and all electrophysiological signals which are produced by the parts of our organism, the systems of which are part of our body, actually have fractal properties, and they are fractal in nature. They are also not regular. And obviously, if you want to analyze those systems which have fractal nature, for example, cardiovagal control, which is very important in regulating our heart rhythm, has connection with our psychological states and how our brain is functioning. So this close connection is also telling you that internal control mechanisms are also fractal in nature. So they are not regular, and you have to learn about that more. So to conclude this video, I would just say that I'm really thankful to Benamanda, who was visionary and who actually collected the knowledge of all the mathematicians of the end of 19th and the beginning of 20th century, packed it together and enable us to see how applicable it is in every segment of our life. In the next video, I'm going to talk about Professor Vladimir Klonovsky, who influenced me in similar way as Mandelbrot. Thank you for listening.